Firstly, thank you for the invitation. When the head of the regulator asks you to, you'd like to do a slot on broken rails, yeah, and at the Albert Hall, how could I say no? So welcome. Last, you'll be pleased to hear, hopefully, well, it's definitely not least, my challenge will be to get this in 25 minutes, but there's a lot in it, but it's going to be a canter through the broken rail journey, really. Some of the challenges, some of what we're doing, what we have done, but perhaps where we need to take things going forward. So the favourite slide, I've yet to put a presentation up without it in. It looks quite good there. We ran at about 750 broken rails a year for 50 odd years, 40 years from the 60s. That runs through from 1962. That was quite acceptable. 750 broken rails, quite normal. Hatfield, we were up to 952 in 1999. And you can, if you look back carefully, plot some of those through varying levels of investment, where you start to push the assets harder. So yes, we got to 952. The following year, 3 months after I joined Railtrack at the time, we had the accident at Hatfield. So having joined as a metallurgist with a specialisation in rolling contact fatigue, things suddenly got rather busy around October 2000. One of the things we did look at, and probably one of the biggest benefits, make sure you can classify them. We had lots of broken rails. We knew fairly much how many we had and where they were, but did we really know what caused them? So building up systems here, this is an example of our defect management system. We've got something there that goes right through a description, captures a whole load of information about location, age of rail, that side of things. Being able to put them all in a system there, get that used, make it so it's a friendly tool for the front line. They like using it, it makes their job easier. You get adoption. Make it as a chore, make it as something they've got to do for recording purposes. Very difficult sell, but making a tool there that we got them to write it, what does it do? It's still there 15, 16 years later, which perhaps a testament to getting it something that's actually successful there in the system to record that level of information. Understand what causes that. So lots of work we can do to prevent. How can we change what we're doing? Think about that. So a lot of it is a sort of circular process. Monitor it, measure it, analyse it, change things, change controls, keep repeating it. Some of the ones are easier. Tackle the bigger issues, the higher risk ones. So it's easy to chase numbers down early on. There were some quick wins. It gets a lot more difficult. It's not something that's happened quickly. That's 24 years of data there with those reductions. So it's quite a challenge. Understand what breaks them. From our point of view, we try and, or fairly simple explanation, defects in the head of the rail. So transverse defect under rolling contact fatigue from the surface, internal defects, attachment valve from impurities in the rail, defects under a weld repair. End result, same. Something there we can do quite a bit with, relatively easy to inspect, close to the rail surface. So a lot of challenges there. Some of the other ones, rail foot. Our biggest cause of broken rails, I'll say a bit more about them, but you can see there, we're chasing a very small defect in the worst place in the rail, furthest away from the head where we try and put the sound in. So quite a challenge, how we perhaps reduce those further. Some of the other bits we do, welds. Pleased to say predominantly they're old welds that are breaking. We used to run about 30–35% of our brakes were welds. We're now down to about 10 or 11%. So it's a slow process getting rid of all the old ones through sort of natural attrition and breaking them. But it's been quite a challenge over the years, developing improved training, competence, processes, working with our welding suppliers, big changes in the industry, in the quality of welds. So what we're putting in now, failure rates are running at about 1 in 50,000, which for a site process in any old conditions, quite a significant improvement on where we were. And you can see some of the things that that broke welds. Some of them I look at and you think, how did it last 50 years? But we wouldn't accept it if that was what we were doing now. So changes there. Perhaps one that we look at, we've done quite a bit of work to reduce these rail ends. Big challenge here and quite high risk. Unlike some of the other breaks, you can see are fairly vertical. Big chance of a piece coming out in the rail head there. And if you go back in time, there's a whole catalogue of tragic accidents associated with broken rail ends, broken fish plates being fouled. So more recently, I think Hither Green in '67 changed things quite dramatically for rail end inspection in the UK. But more recently, I think suburbs of Paris, we had a derailment with a fish plate spun over, derailed a train. Outside of Milan, they had a similar one with a corner crack, almost identical to the bottom one in the picture. That piece of the head got trapped, turned over under the wheel, flicked the train off, and killed 3 people there and over 100 injured outside Milan. So it's worth thinking about the risks. It's very easy to chase all the numbers, looks good, but in some cases, I'd swap 3 or 4 broken foot failures if I got rid of one rail end failure in that situation. Similarly, where they're occurring, so swap off 3 or 4 in a siding or low category track to get rid of a couple in the high speed line. So think about the risk as well. Last few we've got, a bit unusual, some of them. We've got stuff, cast crossings, top left, there's a tri-metallic weld, same with the ones on the bottom right. Difficult weld to join 2 dissimilar materials together, effectively 2 flash butt welds 20 millimetres apart. One side wants to be hot during welding, the other side wants to be cold during welding, and it's always going to be a compromise, but big challenge not to get cooling wrong and then failures. Some of the others, the middle one at the top, arc damage, where we've got short between third rail. So yes, burns big bits out the foot of the rail, very rapidly leads to failure. Some of our others around fabricated units, crossings and similar. And then there's a few like the bottom left, bit of vandalism there where we bounced a road rail vehicle on the foot of a weld. Doesn't do it any good at all if you don't then manage that. Clearly we knew something had come off, we derailed a vehicle, but it didn't get picked up until it was a broken rail. So challenge in that situation that we report, we understand what we've done there, particularly where it's self-inflicted. As I said, classify and understand it all, not just where it is, how many, but a bit more about it. Things like the age of the rail, the conditions around it. Some are quite obvious. This one, clearly a corrosion problem. Big thing I think made a difference for us, take pictures, good pictures, both in situ and close-ups. Quick picture on the fracture face, picture from the side. I don't need to read most of the rest of it. It's a wet tunnel, 3/4 of the foot is missing. You can see where the fracture's gone from the bottom of the rail, perhaps no surprise, but certainly in there, getting those, storing all of that information, putting it all in a database that's accessible, you can interrogate it. So a lot of work, we've got some clever dashboards. It's visible to anyone within the company, covers all of our broken and defective rails, some of our other things like eddy current data for RCF, so big benefit there. If you look at some of the other stuff, I was going to say a bit more there. I thought I'd be really clever and I'll put a slide up here with a few of the key points that made a difference down this timeline. So I started off and I put a few up and it got really difficult. And I've missed a load out and I ran out of room. Don't expect to go through them all. You'll be lucky, you'll be fortunate to hear I'm not going to go through them all. There are some bigger ones in there that did make bigger differences. A lot of them took a long time. Very few of them happened instantly. We apply it and the benefits come years later. But I think the main thing, it doesn't happen instantly. Tackle a whole load of different things. Don't look for one solution. There's no magic wand, unfortunately. Well, I've yet to find it. If anyone's got it, I'll borrow it. But a lot of work there. Some of it is understanding and research, not things you directly think of. Other things are much more related, changes in our inspection, bringing in different controls on joints, that side of things. So it got complicated and, well, it just shows there's a lot of things you've got to keep doing, keep changing, keep introducing in order to get to a point where perhaps driving the numbers. And the challenge now is keeping those numbers down. So it looks good at the moment, and I'm probably tempting fate because that 14 is already out of date by 2 since I've been sat down this morning. So yes, it's not going quite so well, but it's nearly mid-perfect weather of 18 degrees grey with light drizzle. It's almost the perfect track engineer's weather. What comes in the winter, and you can see some of those colder winters or cold early, we run out April to April. So January, February can be very cold. That's what happened 22, 23. We had that very cold start to the year. But it made the following year look good because it wasn't so cold. So a lot of it's a bit weather dependent, but keeping that figures driving down is certainly quite a challenge. If you look at it from what breaks our rails now, this is an average of the last 4 years. The big column on the left, foot failures. So a small amount of corrosion. I'll show some examples. The numbers then come down pretty quickly then. So star cracking at bolt holes, flash butt weld on the stainless steel insert, and then we're starting down into almost single digit stuff. These are the numbers over 4 years, so small numbers. So if you look at saying, well, we want to take 10 more out, you might just say, oh, I'll take them all out, I'll go after foot failures. But generally, they're quite low risk. And I'll show some pictures that explain that a little bit more. The bolt holes, they're getting better, but there's still quite a number. And it's one of those, there's always a risk with a broken rail. It's perhaps quite a small risk with some of them, but the risk is always there. Some of the examples, these are our typical foot failures. We knew we had a weld that was badly dipped, so we clamped it. But the rail on the voiding sleeper there then went from a defect in the foot, very small defect that then fractured. Similarly, another weld next to it. That one, yeah, not the best support conditions. So common factors start coming in here. Understand what is around that. So if you look at everywhere where you've got a small dip, but where the rail is older, where the support conditions are poor, clips are missing, that side of things in the middle of a wet bed, perhaps no surprise if you look at rail in bending there, that's likely to fail from a foot. So a small defect there, and they are small. You can just about make that out. I don't know if the pointer works on this one. But yes, tiny little thing, perhaps the size of my fingernail. Trying to chase that with some sort of inspection is quite a challenge. And a couple more pictures here. Similar sort of failure. But you can see on the underside of the foot there, that's where the pad has been poor condition. Some of that's the attrition because there's a dip and high dynamic loading, but it traps a load of water and moisture. The pad around the outside looks pretty good, but you can see what it's done to the underside of the rail. You try inspecting for that, and there is a crack. You can just see the smooth fatigue areas in the bottom of that rail. In theory, we should see that. You run the ultrasonics over it, you get noise off every one of those little pits and roughness. And we found thousands, tens of thousands of suspects for a few tens of breaks. Which ones do you take out? How quickly can you take it out? We know they break from a small defect. So a big challenge there as to how we do it. Inspection wasn't really making a lot of difference there. We were really struggling to get much from it. So what we did look at, some of the bits were early on, dip angles, we call it. It's the vertical geometry the profile a wheel takes as it transfers over the joint. You can see some poor examples here, poor support conditions around the crossing nose, continuous voiding, and a fatigue crack will start from the bottom. You can see in the top right, it growing up the sidewall, comes up there. There's a lot of things you look at and you think, why did we have scalloped bottom to the crossing? Why do we have different sections underneath? They all act as stress raisers. Put that directly under the wheel transfer area with a load of voiding. You can see in the situation in the bottom right, that voiding you can see often as attrition in the ballast. The ballast is white around there where it's fractured. So yes, understanding that, been a lot of the work has been looking at if we can't find the defect before it fails, what can we do to stop the defect in the first place? So a big bit of work at the moment looking at reducing the dynamic forces and similar. Some other examples of it, you look around, crack in the foot of the crossing, significant voiding, quite a lot of ballast attrition, but we've also got bearer joint screws missing there, broken, so clearly a lot of energy in that situation. Stopping it getting to this condition, because once you get this level of voiding, cracking and eventually a failure is almost inevitable. The physics will destroy the material. And the last one, rail joint, looks okay, it's all sitting there. That one was held by the plates, but you don't need much for it to go at the top of the fillet as well. And as we've seen in a few recent ones, big risk in those because you can get a piece of rail trapped, flick out, turn over in that bit there and lead to a much more serious incident. A little bit on fish plates and where we started with dip angles. If I go back to my previous chart, we took about 150 broken rails out just by managing the dynamic loading back in about 2006. And I know that my boss at the time said, you want to introduce 82,000 new defects onto the network to manage. Yeah, but you don't have to do them all instantly. They'll be prioritised. It's taken a number of years to get in, but it's quite accepted now that we manage the geometry to control the forces. And you can see, nice fish plate, dead straight, forces are all low. Put a step in, particularly a step up, you get some massive diagonal forces in there, and the rails will do what physics says, and they will crack at the opposite direction to the maximum forces. So it either rips the head off, or it goes up through the first or second bolt hole pretty much at 45 degrees. But you do end up with that triangular piece at risk of coming out. So yeah, avoid step joints, avoid dip joints, particularly steps up. And it did make quite a difference. We went from sort of 307 down to about 190. When you look in the data, quite a lot of those were taking out badly dipped joints, which they were going to fail, but hadn't yet. So it did give us an insight there. So fix the conditions that lead to the problems, in some cases more successful than trying to inspect for very small defects that cause the failure. Looking at the numbers here, since 2015, this is part of the thing, and people look at the broken rails and say, that's excellent, really good, coming down, low numbers. These are the defects we're removing each year. So you look at that, we're removing somewhere around 35,000 defects a year. It's about 80 or 90 every day across the network, every day of the year. And if you look at where money sort of side of things, if we can start reducing some of those, we've done well managing some of the broken rails, but some challenges there. If anything, defect numbers are going up. And if you say it's £2,000, maybe 10 grand for the worst ones to take out, you can do a bit of maths, you're in the millions, tens of millions or hundreds of millions there, is where money's going in order to try and manage those small numbers of broken rails. So a big challenge there, particularly what we try and do with that to get those numbers down, because that's a lot of work, it's a lot of access. We tend to now, a lot of our staff in the track world, spending most of their time doing rail defect removal or geometry faults. Little chance to do much else. Preventative maintenance is starting to take and suffer, so what can we do to challenge that? Some of the things we are doing, some of the things sound obvious, and they've been happening for a while. We've had some big success putting camera systems on some of our trains. We fitted it to one of our ultrasonic test cars. We've got it on a number of other vehicles. It's fairly straightforward. It looks complicated. It's just a series of cameras at different angles, some clever lighting. The clever bit, and what I've seen change even in the last few years, is how fast we can get data from that train up to the cloud, processed, and back down again. So most of the time now we're running one of our UTUs with it fitted. It does all the ultrasonic testing. The vision system has processed all the data, provided images of all the suspect locations, and that's not just the suspects we get finalised, that's every suspect that the machine on the night that gets discounted and analysed the following day is ready on the doorstep of Sperry by about 8 o'clock in the morning. So very clever where they're going with the processing data. And what I've wanted to do for a number of years is suddenly, I think technology, machine learning has caught up, and it can do things in minutes that would have taken days and weeks to do previously. So some quite exciting stuff there. There's some examples of the AVA system. It not only will give you an image of all of the rail, it will then, using AI, do a whole load of stuff. And basically, if you can see it in a picture, the AI learning, with a bit of training, can then pick them all out for you. So instead of looking through miles of video, it just gives you a whole list of them all with the pictures. You can look at what you've got there, and certainly some of the engineers out on the ground are putting a lot of effort into training it, but it's really making quite a difference. And we're finding now that a lot of our defect surface damage is visible in the video well before we see anything in either eddy current or ultrasonics. So it does give some opportunities to start fixing things before they're really defective. So a bit more preventative rather than reactive. Some of the other things we're looking at, and it's really, I've always said we're data rich, but turning that into good information has always been a struggle. So one of the things we are doing, Insight, it's a system that basically brings a lot of our existing data streams together, realigns it all by a common location, and then puts it in a system where it's easy to store all the history. You can then apply queries to it. So I can say, I want to see all of the dip welds in 1982 rail on the West Coast main line that have carried 7, and there, suddenly it's all there. It's hugely beneficial. It will, I think, give me a chance to get out and escape. I won't be doing spreadsheet engineering, it will do it all for me. So hopefully, we still got to then use it to fix it, but there's geometry, whole load of runs at different time scales all aligned over the top. You can then look at things like dips here, these are dip angles, and you can look at the deterioration rate, you can see it increasing over time. With a bit of confidence, you can then start to make forward predictions as well. So if you know it's growing at this rate, you can say, well, it's going to reach a threshold or a critical limit in 6 months' time, not waiting for it to get there. So some work there, and some of them, yes, they do jump up very suddenly and increase, but generally we can predict it, and with the frequency of data we're getting now, we can start to draw these progressive sort of deterioration plots quite quickly now, quite reliably. A few other bits there. There's an example, a squat or a small bit of surface damage on a flash butt weld. We're linking this, we've got that. We've got some superb pictures, considering this is taken at speed at night. Though you can zoom in, once you've downloaded it, you can get into a huge amount of detail. That's the B scan. That's all we had before from the ultrasonics, a little indication. Put the two together, we go out and verify that, put a paint mark on the side of the rail so the welders know where to come and fix it in 3, 4, 6 months' time. With this sort of level of confidence, do we need to go and visit it? We can look at this, we can look in Insight, we can scope the work, we know what rail it is, what wear, what depth, where exactly it is, we've got a picture. Perhaps some opportunity here to start changing fundamentally some of the things we manage. So train-based inspection, we get a whole load of suspects, we go and check them all, we go and mark them all up, we go and look at them. With the eyes like this, it gives you sort of eyes on a U to for the first time. And it's already making a difference in that our analysis of the data, they can discount things like welds, which show some signals. We would previously go out to that many times. They can discount that at source. They're confident what they're seeing, so it's made a big difference to the ultrasonics. It's given them this two source of information to confirm something. So some quite exciting stuff with it. Some clever systems, but the big clever thing, it picks all of these out for you. It marks them all up. You don't have to go through the miles of data. I've spent some exciting Saturday nights, although my wife's convinced my choice in television watching this sort of thing is not the thing for mainstream Saturday night, but it floats my boat. But I've tried and I've gone through it and thought I'll pick every weld out, every joint out, everything I can see and see what the system's done. And it keeps beating me. I can't concentrate enough to do it, I think, and it can cope even when the resolution is poor or the contrast is poor. Maybe that's a fault of my eyesight on things, but it's surprisingly good, and it doesn't care, it doesn't get bored, and it does hundreds of miles in a minute, whereas it took me 5 hours to do about 8 miles carefully. But yeah, some quite impressive stuff. The more we can teach it, the more it's doing, and we've already getting to stuff now. You link the B-scans, you put it all with the joints, you start understanding a whole lot more about the rail condition. The machine learning there, and this is a couple of examples. It puts all of this stuff in and just detects it all and says, here's all of your things, here's all of your bits and pieces. So you've got welds, conduits, orange pipes, crossings, switches, welds, whatever you want. If you can see it, train it, it does it all. And it says, there's a big run. So we've done however 150 miles of testing. And it's turned around and said there's over 3,000 thermit welds. Take you hours to do that, days to do that. But fantastic that it put a whole lot in the register there. Stuff I've sort of dreamed about for years, but happens in minutes. And then you take it to the next level and say, oh, I want particular defect types or severity of damage, or even they're linking it to geometry as well. So I want to see my joints with lips and dips, and you can't play tunes forever. And then it says, do you want to worry about the crack in the fish plate? And you think, yeah, definitely. So yeah, some huge step forward with that. What's being done now, that's making more difference in the last 6 to 12 months. It's things we wanted to do, and I think we thought were possible, but suddenly become fairly easy with the intelligence and the machine learning. And it's not something that's taken weeks and weeks and weeks of teaching. It will pick out all of the stuff and say, right, you sit through and tell me what all of these are, and then I'll know, because it's done all the hard work picking out all the unusual images. So yeah, the future, some of our stuff with the infrastructure monitoring program running at the moment, big push to see what we can do on trains. Why are we running a whole yellow fleet? I think we've got 18 yellow and some blue vehicles running at the moment. How much of this can we put onto revenue vehicles, onto passenger trains? We're just starting to roll out UGMS, the unattended geometry measurement, on a number of the Class 800s on East Coast, on Great Western now, and that's starting to, I think, make a difference and potentially gives us geometry information daily, many times daily. So if you've got the right systems to absorb that data, you're not having to go and look at it every single time for all the repeats. It gives you a lot of information. So some big challenges. What can we do on more revenue vehicles? Location going to become key. So a lot of work we're doing with alternatives to things like GPS and similar to try and map our network. We have a system on trial that videos all the sleepers and all the ballast. You then have a map on your phone, you show it a picture, and it says it's that way or this way to wherever you need to go to. Works tunnels, anywhere at all. No need for any GPS or any connectivity as long as you've downloaded this base map. But it just re-looks at the track every time it goes past, memorises all the ballast positions. You show it a picture of a bit of ballast and it tells you exactly where on the network that is to within about 10, 15 millimetres. So will it work? Hopefully. We're getting there, but the trials look pretty good at the moment. We just got to link the whole lot together. So common location becomes key. Big things going forward. I think we can get a lot of boots off ballast. We send too many people out to look at stuff now. We're pushing a lot of those inspections into night time to separate people from trains. And to be honest, if you're out in the middle of the night with a torch trying to look for small cracks in the foot of the rail, it's not easy. And I've shown pictures to people and they're absolutely horrified they've walked past it. They can't believe they've missed it. Yet we've got a video image there that shows it was very clearly there. But I think human nature is humans aren't very good at looking for things by exception, particularly if the lighting's poor and that sort of stuff. You're very clever. You can fill in loads of detail that you can't actually see. But the human brain, the eyes will make up a load of stuff. So if it looks like a crossing and it's in the dark, yeah, it's got clips. Yeah, the clips were there, sleepers. couldn't see any of them, but it just puts it all together anyway. So it's a phenomenal bit of interpolation, but perhaps not always good if you want an ideal visual inspection. So a few things there. Why are we concerned by broken rails? Fortunately, most broken rails don't result in a derailment, but just over 24 years ago, broken rail at Hatfield on the high rail of a curve derailed a Leeds train on its way going north. Unfortunately, it turned over in the middle of the train, wrapped round an overhead gantry and killed 4 people. So it's a sort of stark warning. Whilst broken rails and derailments from broken rails are hugely rare, that risk is always there. Track very rarely fails safe, unfortunately, unlike other systems. First we may know is a driver reports a rough ride. Train's already gone over that broken rail. So the more we can do, the more we can manage, the safer things remain. So thank you very much for the invitation. Just about. Thank you.